Okay, we're continuing our problems about finding the intervals for which function is increasing and decreasing. You can see this problem says find the critical numbers and decide where f is increasing and decreasing if f of x is x minus 2 to a power of 2/5. So as we go through here, the first thing we need to do is find the derivative. Find the derivative because we need to know the critical numbers. So we have to use the general power rule, which says bring the exponent down. Okay, put it in front of the parentheses, decrease the power by 1. So we have to calculate 2/5 minus 1. Of course, that's 2/5 minus 5 over 5, which is negative 3 over 5. So the new exponent is negative 3 over 5. And then don't forget, we have to multiply with the derivative of what's inside the parentheses, and that derivative is 1. So we have f prime of x is 2/5. Oh, let's see here. Let's rewrite this so that we don't have a negative exponent. And so that's 1 over x minus 2 to the positive 3/5 power. Now, we would probably go to simplifying this just a bit more. So let's rewrite this derivative. F prime of x, we see that we have a numerator 2 times 1, and we have a denominator, which is a 5, and then this x minus 2 to the power 3/5. Well, remember that 3/5 exponent means that we have a fifth root, doesn't it? That's a fifth root, and x minus 2 is under that radical, and that 3 tells us that we end up having what? A power of 3, that is the 3 in the numerator of that exponent, a power of 3 on that radical. Okay? Now, that's the derivative. That was a little more detailed than normal. To find the critical numbers, that's what's next. And so if we're looking at the critical numbers, we need to know where the derivative is 0 or where the derivative is undefined. Whoops, is undefined. Okay, the derivative is 0. If we look at this, that's what we would be setting to 0 is this monstrosity here, right? Say fifth root of x minus 2, and of course we could have the exponent 3 on the radicand or on the outside like we've got it, equals 0. But we'd really need to be a little more adept than this, because no matter what we put in for x, we're going to, I guess we could get a 0 in the denominator. But if we put anything besides 2 in for x, we're just going to have a number in the denominator, and 2 over a number is never 0. So there's no solution to this. There's no x value for which the derivative is 0. No x value for where the derivative is 0. Now, on the other hand, when we looked at this derivative, okay, what we're worried about is how can something be undefined? Well, it can be undefined if the denominator is 0. And I think that we could look at this and we could decide, look, if x is equal to 2, we'd have a 0 under the radical, and the fifth root of 0 is 0. And 0 to the third power is 0, and 5 times 0 is 0. We'd have a 0 denominator, wouldn't we? So x equal 2 is where this is undefined. And that's the only value for which it's undefined. Remember here, we have a fifth root, so it's all right to have negative values under the radical. Okay, that makes sense. If it was a square root of fourth root, it wouldn't. But we're all right here. So here we are with one critical number, x equal 2. Now, here's what we have to do then. We use that x equal 2, there's x equal 2, to break it into intervals. That is, we're going to look at the interval from negative infinity up to positive 2, and then we're going to look from 2 to infinity. So that's where we're looking at. Now let's go ahead and kind of build this table that we've seen before. I'll keep changing it a little bit at a time. Now remember, what we're going to first do is consider the derivative. And we're really testing the derivative. That's really the first thing we're doing. And then after we make those tests in each of those intervals, then we're going to draw our conclusion. That's really what this boils down to. What's the conclusion about the graph of f? That's the whole point here, the graph of the function f that we started with. So we need a test point between negative infinity and 2. And so I'm going to choose x equals 0. That's in between negative infinity and 2, isn't it? And so here's what I'm needing to do then. We're needing to evaluate f prime of 0 and see whether we have a positive or negative value. So that means we would put a 0 in for the x. And remember, this is what our radical looks like. And I think, well, let's go ahead and I'll write it like I have. So it's the fifth root, and we have a 0 minus 2, and that's raised to the third power. Okay? Now, I don't need to calculate the value so much. Here's what I'm needing you to think about. I just need to know whether this is positive or negative. And so what we're having here is a fifth root of negative 2. 0 minus 2 is negative 2. And that's raised to the third power. Okay, so once again, let's stop and think about this. The fifth root of a negative number is negative, isn't it? So we have a negative number in here that's being raised to the third power. Well, that means when we raise a negative number to the third power, negative times negative times negative is negative. So here we have 5 times some negative number. Well, it boils down to then, on top we have a positive number, on bottom we have a negative number, and so the fraction, regardless of the numbers, is going to be negative, isn't it? So that's really all we needed to know. When x is 0, we know that f prime of x will be negative. And if the derivative is negative, then the function is decreasing. Now we need to choose an x value that is bigger than 2. Okay, bigger than 2. So I could choose x to be 3. So when I choose x to be 3, then I'm looking at f prime of 3. I want to know if it's positive or negative. So I have 2 over 5 times the fifth root of 3 minus 2, and that radical then is cubed. Well, that's not going to be hard to figure out because 3 minus 2 is 1. So this is the fifth root of 1 raised to the third power. But the fifth root of 1 is nothing more than 1. So now that's 1 to the third power. Of course, 1 to the third power is just 1. So this ends up being 2/5. Here the number was easy to calculate, but what is important to us is that that is a positive value. So when x is 3, f prime of x is positive. And so that means the function is increasing on that interval. Well, if the function is increasing, and remember, we know that all we need to do is test one point because 2 is the only place that it can change. So that we know it's not going to change anywhere from 2 to infinity, and so one value is enough to test. Okay, so we can come up with the final question then. Is the critical numbers we found, critical number was 2. Okay, that was one of the things we were supposed to figure out. We found that. And we find out that it's increasing on the interval. What? Let's see. Here's where it's increasing. And so that interval is 2 to infinity. It's increasing on the interval to 2 to infinity. and it's decreasing. So we decide here it's decreasing, and what interval is that? Negative infinity to positive 2. Negative infinity to 2. So there we've answered the other part of the question. Well, I think it might be nice just to look at this graph also. And so I'm going to pause so that I can get this graph up for you to look at, and then we'll continue after that.
Okay, here we see the graph. Remember, this is the graph of f of x equal x minus 2, the quantity to the power 2/5. And one of the significant things I want to point out to you is on this graph, we found that the critical number came from where the derivative was undefined. And the critical number was 2, and so it's very significant here to understand what that picture looks like. When we have an undefined derivative, we can anticipate certain things happening in the way it looks. And in this case, the way it looks is a point. We call that actually a cusp that we see there. So it's not a smooth transition. It's not kind of a peak or a valley. It's a very quick transition, and we have that pointed cusp. So that's a significant thing to see here. Also, we understand that as we look to the right of 2, the function is in fact increasing, and if we looked at the left of 2, the function in fact is decreasing. And so that's very important for us to see here. Okay, let's pause for just a moment as I get set for the next problem.
Okay, we're continuing our problems about finding the intervals for which function is increasing and decreasing. You can see this problem says find the critical numbers, and well, again, we continue. Here, it seems our functions are getting more complicated. For the function f of x equal the square root of 3x squared plus 1, find the critical numbers and the open intervals where the function is increasing or where it is decreasing. This is what we've been doing. Open intervals is just a new word that's thrown in here, but that's exactly what we've been doing. Okay, so we know that this starts out with needing the derivative. Okay, that's what we need to do, find the derivative. Now the function f of x isn't a good form to find the derivative, so first thing we're going to do is change the form. That is, we're going to change that square root into an exponent. So we'll say 3x squared plus 1, but rather than the square root of that, the power 1/2 on that. Okay, now we're ready to use the general power rule to find the derivative. So we bring the exponent down, times 3x squared plus 1. We decrease the exponent by 1, and so the new exponent is negative 1/2. But then we have to multiply with the derivative of what's inside, and the derivative of 3x squared plus 1 is just 6x, isn't it? Okay, so now we're going to spend some time kind of putting this together and making it look better. Well, we have a 1/2 times a 6, which is a 3, and then times an x, just put that in front, but this negative exponent means it's 1 over 3x squared plus 1 to the positive 1/2 power. But that really means we have a square root in the denominator. So 3x times this fraction will have a 3x in the numerator and a square root of 3x squared plus 1 in the denominator. So there's our derivative. I think to save space, I'm going to come over here now. So the next thing we need are the critical numbers. Those are the boundaries, aren't they, where we change from increasing to decreasing or vice versa, if it's going to change. And we've seen that it doesn't always change. Okay, so what we want to know is where the derivative is equal to 0, or the other way we can have critical numbers is the derivative is undefined. Well, for it to be 0, we'd have 3x over square root of 3x squared plus 1 is 0. Now, there's several ways we can approach solving this. We can multiply both sides by the denominator. So we'd have square root times fraction. Whoops. I really bungled that. That's like over 1, really. I'm multiplying by the square root. So we're multiplying on both sides by this square root. Now over here, of course, the square roots cancel, and we have 3x. Over here, we have something times 0, which is 0. Now, I want to point out to you that really way up here, we said, okay, we have a fraction that's equal to 0. And I want to remind you that a fraction can only be 0. The only way it can be 0 is if the numerator, if the top 0. Some number over a denominator is always just a number that's not 0. The only way we can get 0 is 0 divided by a number. So you see that's what we really have here is the numerator 3x equal to 0 is what it boiled down to. And then of course the only way that can happen is x equals 0. So x equals 0 is a critical number. Now, we go back and we look at this fraction and we want to know if the fraction, is f prime of x ever undefined. So we're looking at 3x over 3x squared plus 1. Well, what we would be worried about being undefined would be two things. Are there x's that cause a negative under the denominator? Or are there x's that cause the denominator to be 0? And because we're dealing with x squared, no matter what x we put in there, when we square it, we'll get positive, won't we? Or maybe 0. And then 3 times that number will be positive. And then that positive plus 1 will be positive, so it'll always be the square root of a positive number. Even if x is 0, we just have the square root of 1. So there's no way we can make the denominator 0 because we're always going to have at least 1 more than 0 under the radical. And there's no way we can have a negative under the radical, so there's no place that this is undefined. Okay? There's no place that's undefined. So we have one single critical number, x equals 0. Well, that doesn't usually we have more than one critical number. We're seeing a lot of cases where we just have one. But usually we have more than one. But anyway, here's where 0 is. And so we have the values of x that are less than 0. That's negative infinity to 0. And then we have 0 to infinity. Okay, so we build this table once again. First, we're worried about f prime of x, and we're testing. That's what we're doing here, is we're going to test f prime of x, and then we'll draw conclusions. The graph of f, not of derivative, is what we're drawing conclusions about. So we've got to pick a number that is between negative infinity and 0, which means it's negative. Okay? Now, we can pick a number or we can be analytical. So just imagine if we take the derivative and we put a negative number into it. Well, on the top, we'll have 3 times the negative number, won't we? And on the bottom, we'll have the square root of 3 times a negative number squared plus 1. So what I want to get you to realize is 3 times a negative number is negative. So on top, we have a negative number. But on bottom, we have the square root of 3 times a negative number squared, which will be a positive number, won't it? So on bottom, we have a positive plus 1 square root of. On bottom, we will end up having a positive number. So the fraction's negative divided by positive, and that's just going to be negative, isn't it? So without even testing a number, I'm deciding that the derivative is negative in this interval. Now likewise, if I'm thinking about choosing a value between 0 and infinity in the interval 0 to infinity, that just means a positive number. So I imagine putting a positive number into the derivative, and like before, it'd be a 3 times a positive, and on bottom it'd be 3 times a positive squared plus 1. everything's positive. There's not any subtractions. Everything's positive. Be positive on top, positive on bottom, altogether positive. So without even testing a number, we know that the derivative is positive in this interval. I said greater than 0 and less than 0. Remember, that just means positive, and that just means negative. So here we know in the interval between negative infinity and 0, we're decreasing. The graph is decreasing. And between 0 and infinity, the graph is increasing because the derivative is positive. We could summarize that. Once again, I want to pause and show you the graph. We've got the information we need. We know the critical number, and we know the intervals that it's increasing on, and we know the interval that it's decreasing on, and we could just write that up. So we'll pause here and show you the graph of this just so that it fits together.
Well, here you see the graph. Looks a bit like a parabola, but it's not. Remember, this is f of x equal to the square root of 3x squared plus 1. And just to put a few pieces together, a square root will always be a positive result, won't it? And so you see all of our y's are positive. Our x's can be negative, but our y's are positive. And our x's can be negative because once we choose an x value that's negative, like we see here, when we square it, it ends up being a positive value. So we end up with a square root of a positive number no matter what. So anyway, here's what it looks like when there's actually a little bit something wrong with this graph as I'm looking at it now. I hadn't noticed that before. Anyway, our graph does look something similar to this. Apparently this isn't exactly the correct graph, but you do get the idea. X equals 0 being the critical number, so to the right of 0, when x is greater than 0, the graph is increasing. To the left of 0, when x is smaller than 0, that's out here, of course the graph is decreasing. And that's what we needed to see in this example.
Okay, the last problem of this part is just a change in the function type. Find the intervals for which the function f of x equal x plus 3 over x plus 5 is increasing and for which it is decreasing. And we know that we need the critical numbers to do this with, and so we look at the derivative. Okay, and that's the first thing we need to do is find the derivative. Oh, well, to find the derivative here, we've got to use the quotient rule, don't we? Quotient rule says take the take the denominator, which is x plus 5, and multiply it with the derivative of the numerator. And of course, the derivative of x plus 3 is just 1. And then subtract. And what do? We take the numerator, which is x plus 3, and multiply it with the derivative of the denominator. And the derivative of x plus 5 is just 1. And then we divide all of that by the denominator squared. Well, we need to do some major cleanup here, don't we? We end up with a x plus 5 times 1, which is just x plus 5. And then we need to, let's kind of look at this. I'm thinking when we take this, I'm just looking at this part of the numerator, times the 1. I'm really thinking, oh, well, that's just negative x plus 3. And that ends up being negative x minus 3, doesn't it? So here we have a minus x minus 3, and that's all over x plus 5 squared. And then above, x minus x is 0, and 5 minus 3 is 2. So this simplifies to f prime of x is 2 over x plus 5 squared. Okay? Now, next thing we do is find critical numbers. And we find critical numbers by finding out where the derivative is 0 And other critical numbers would be where the derivative is undefined. I'm going to address the critical number, the derivative being 0. Remember, the derivative is 2 over x plus 5 squared. And what I want to remind you of, so where is that equal to 0? Remember, the only way a fraction can be 0 is if the top is 0. Because no matter what x's we put down below, we can't choose an x that's negative 5, because that would be a 0, wouldn't it? But any other x, we're just going to have a regular old number in the bottom. 2 over a regular old number can't be 0. See, the only way a fraction can be 0 is if its numerator is 0, and there's no x that makes 2 0, is it? So there are no solutions here, which just means there are no critical numbers associated with the derivative being 0. But now, when we look at derivative undefined, so once again, the derivative is 2 over x plus 5 squared. Now, the only way this can be undefined is if the denominator is 0. And the only way the denominator is 0 is if x plus 5 is 0, and that would be when x is negative 5. So if we put a negative 5 right there, then we get 0 squared on bottom, which is 0. So it's undefined when x is negative 5. So again, and we're going to have more cases where we have more than one critical number, but in this case we have one single critical number again. Okay, there's our critical number that it didn't ask for, but now we're going to test, aren't we? We're going to test f prime of x. And based on the test for f prime of x, we find out when we're increasing and decreasing. So I'm thinking, here's number line, here's negative 5, and so in here is from negative infinity up to negative 5, and here is from negative 5 to positive infinity. Now we're really worried about testing f prime. I'm getting lazier and lazier. And after we test f prime, then we know about the graph, not of f prime, but the graph of f. That's the whole purpose, is we're trying to find out about the graph of f. So we need test values. Well, I'm going to, this is what you recognize, that is we want to think. We don't always have to calculate if we think a little bit. Now, look at the derivative, 2 over x plus 5 squared. And I guess what I'm wanting to mention to you then, recognize to you, it really doesn't matter in the bottom whether we end up with a positive or negative in the parentheses, because we're going to square it. So what I'm getting at is that we're always going to have a 2 on top, and we're always going to square a number on bottom as long as it's not 0. And so always on bottom we're going to get a positive, aren't we? So f prime is positive for no matter what x we choose. It's positive whether we choose an x that's less than negative 5 or bigger than negative 5. We can't choose x being negative 5, but if less than or bigger than, we'll always have a positive on bottom. So that tells us that the graph is increasing and increasing. So it tells us the graph is always increasing, isn't it? We've seen this idea before then, that it never decreases, and it increases everywhere. And that would mean from negative infinity to positive infinity. Okay, so there should be our result. Okay, well that ends this part. And I guess I'll get a graph up here and we'll look at it real quickly. Oh, by the way, I really fibbed a little bit here. I apologize. If you read your book and you read the literature, it's going to tell us that that's not a critical number, and x equal negative 5. And the reason it's not a critical number is the original function's not defined for that. See, x can't be equal to -5 to begin with. -5 is not in the domain of the function. And so that means we can't ever use -5 to begin with. Now, it's still an important place where the function's undefined. We've seen before, when the function's undefined, not just the derivative. When the function's undefined, we might have a change from increasing to decreasing or vice versa. So even though the function is not defined there, neither is the derivative. And in this particular case, I call that a pseudo critical number. It doesn't follow the facts of being a critical number by a law. That is, the law requires critical numbers be in the domain of the function. And it hasn't been an issue till now. But we're going to treat it like a critical number. Okay? And treating it like a critical number will give us the results we want.
Okay, here you can see the graph of f of x equal x plus 3 over x plus 5, which isn't a complete surprise. And again, I want to point out to you, of course, at x plus 5, at x equal -5 is where the function's undefined. Earlier, we would call that a vertical asymptote. So we see that vertical asymptote in the red dashed line there that's not actually part of the graph. I want to remind you again that in this case, we found the critical number as being the x value for which the function was undefined. And so when we find where the derivative is undefined, certainly can be a place where we have a change, can be a place where we have a change for the function increasing, going from increasing to decreasing and vice versa. And again, I want to point out that when the function has a derivative that's undefined, we have something a little different than a normal peak or a normal valley. And that's illustrated here. But as we saw earlier on, here is the critical number x equal -5, and we considered, we tested and found out that the function was increasing, and here we see that of course it is increasing from -infinity up to -5. Now on the other side of -5, of course that's over here, we look at the graph and it is also increasing, and that's exactly what we found in our problem, isn't it? So this, again, we're trying to do this without the aid of looking at a graph, but it's nice to verify our findings with the graph after we've done the analysis.
Oh, this is a very special type of problem, and it really makes us have to think outside the box a bit. What we're looking at below, or what we're looking at here, is the graph of a derivative, not the graph of the original function, the graph of the derivative. You know, when we find a derivative, it gives us a function, and we can in fact turn around and graph that function that we got. We can graph that derivative, and that's what this is. So, as it says, below is the graph of the derivative, f prime of x. Use this graph to decide where the graph of f, the graph we don't see, where is the graph we don't see, the graph of f, increasing? Okay, so where is f of x increasing? So we can't come over here and look where that function is increasing because that's f prime of x. Here's what we need to recall. Think about this. Think in this way. F of x increases when the derivative is what? When f prime of x is positive, right? The graph of f increases when f prime of x is positive. We could say greater than 0, but what we really mean, of course, is that f prime of x is positive. Now, let's use that to think about what's going on over here. Okay, now remember this is the graph of f prime of x, and so f prime of x is like the y. See, here's the x value, but y is f prime of x. So where is f prime of x positive? Well, that means where are the y values positive? And of course, the y values are positive on this part of the graph. That's where f prime of x is positive, and the y values are positive on this part of the graph. Okay, those y values are positive. Well, what x values are those? Those are the x values that go this direction, aren't they? So look at this. F prime of x is positive when x is greater than 3 and when x is less than -1. See out here. For those x's, we're talking about this part of the graph. The x's out here, we're talking about that part of the graph. For the x's out here, we're talking about this part of the graph. Well, then that would be the interval. So f of x is increasing. See, f of x is increasing then for these intervals. From -infinity to -1, and from 3 to infinity. Now, the next part is obviously very similar. Where is the graph of f, that is f of x, decreasing? Don't look at the graph right now, because that's not, what we're looking at there is not f, it's f prime. We need to think again, though. What does it mean? How do we find out where f is decreasing? Well, the way we find out is that we look at the derivative. So f prime of x being negative, that is less than 0, negative is when f of x is decreasing. And now we're looking at the graph of f prime of x. So when we say, okay, well, where is f prime of x less than 0? What we mean is, what part of the graph is y less than 0? And for the part of the graph down here, it's always below the x-axis, so the y's are 0, aren't they? And so we're referring to then that it's these x's on this part of the graph, these x's are the x's that give us y's or f primes that are negative. And of course, that's the x's between what, -1 and +3? So f prime of x is less than 0 when x is between -1 and +3. Well, of course, the way we write that is we write it as the interval from -1 to +3. So we're decreasing, see, we're decreasing on the interval from -1 to 3 by looking at the graph of the derivative. Very interesting problem. In fact, I think what I'll show you is the graph that we just looked at of the derivative and actually the function that this graph came from.
Okay, here we have both graphs. The blue graph is the graph we saw that we were analyzing, and the blue graph represents the derivative of f. That's that graph. The red graph is actually the function f. And so the significance here, of course, is that we looked at the blue graph to make the decisions. And what did we decide? We decided that the red graph, the graph of f, was increasing from what, -infinity to -1. And look here, the graph is increasing until it gets to -1. So it increased from -infinity up to -1. And then we also said the red graph was increasing from 3 to infinity. From 3 to infinity. We'll look at the red graph. When x is 3, we're here, and as x gets larger and larger, then the graph is in fact increasing, isn't it? And we also said that the red graph was decreasing from -1 to +3. Well, we look at the red graph, that's the graph of f. In fact, we are going down, we are decreasing. It is decreasing from -1 to +3. Now remember the way we did that. We were only looking at the derivative, that's the blue graph. We were only looking at the derivative. And what we decided is when the derivative is positive, that means when the derivative has y values that are positive. That means they're y values that are above the x-axis, doesn't it? And so it was for those x's that caused that to happen. And so here's where we started having the blue graph have positive y values. And so that meant the x's that went with that were -infinity to -1. So positive y values on the blue graph indicate increasing, that is, this is positive derivative, that meant increasing function. And then we found out that when the graph is below the x-axis, that meant f prime was negative. Those are negative y values. When we have a negative f prime, then the function's got to be decreasing. And so we knew that it started being negative at -1, the y's, and stopped being negative at +3. All of those are below. And so we had to know that the function was decreasing because those derivative values were negative. And then the blue graph started going above the x-axis again, which meant f prime was positive. And so as soon as the blue graph goes above the x-axis, then we know that our function has positive derivatives. And so if it has positive derivatives, then it has to be increasing. Amazing, isn't it? Well, that does in fact end this part. We'll begin to, I may have another part that is a word problem. If so, we'll look at it. Otherwise, we'll be ready to go on to the next section.